everyone, this is Himanshu, and in this lecture we will study about the stars and black holes. Now, before learning about the black hole, we should know what the stars are and what are the forces in that star. So, all the stars have mass. Some stars are massive, and because of this, they have a very strong gravitational pull at the center. This gravitational pull is responsible for the kinetic energy, which is from the mass being compressing the mass of the star in the form of hydrogen, which leads to the motion, and thereby that is called the kinetic energy. Now this kinetic energy leads to the fusion reaction at the core or at the center of the star. So like if this is a star, that is a very bad circle, but this is the center. So there are two forces, the one which is towards the center and the another force which is outwards. Now the fusion is happening inside. Now these fusion reaction take place at a very high temperature, and they require such a high temperature because the two nuclei combine to form the another nuclei, and these nuclei are positively charged, so they both will have a strong repulsive forces between them. And to overcome these repulsive forces, we need a very high temperature. And when the two nuclei combine to give a heavy nucleus, all neutrons of the nuclei, they will become the part of a heavy nucleus. Some are left behind, and those will burn up. So this is also contribute to the high temperature to the fusion. Now generally, these two forces, if we talk about, the one of them is what we call as a radiation force, and the other one is what we call as the gravitational pull. Now there is a very strong gravitational pull at the center which may collapse the star. That is basically the process is called the implosion. So you should take notes as I'm speaking because there's so much content, right? So basically the collapse of the star is what we call as an implosion, but it is not happening because there is some force which is also opposing the gravitational pull, and that means the force which is in outward direction, and that force is called the radiation force. Therefore the both of the gravitational force and the radiation force, they balance itself. So this is a star actually, and this one and this one, they are balancing each other. Now the fusion reaction that is happening in the core, the hydrogen nuclei combine to give the helium. So basically it is the hydrogen which basically combine to give the helium. Now the helium will surround the core. The temperature in the core goes high. At more higher temperature, even the helium nuclei will fuse to the carbon, and so the temperature will also keep on increasing, and therefore balance of the forces will be affected. So even at the more higher temperature, the carbon nuclei itself will fuse to the oxygen or on the neon itself. So as the the reaction and the nuclear fusion take place and the temperature reaches high, within the star, the hydrogen to the helium, then helium to the carbon to the oxygen, and the neon will take place. Now, and interestingly, we always take the mass of the sun as a reference when we compare a one star to the other star. The sun is always our reference. So what we generally consider that if the mass of any star is 0.5 to 0.8 times of that of our solar mass. Solar mass is basically called the sun mass itself, right? The fusion reaction will be slow because the gravitational pull won't be so intense. So if the mass of the star is 0.5 to 0.8 times of the solar mass, so we can say that the fusion reaction will be low. So in this case, fusion reaction will be slow because the gravitational pull won't be so intense. So the kinetic energy will be less, and the fusion reaction will stop at the hydrogen and the helium stage itself that we have discussed above. Now because of this, there won't be an electromagnetic energy, or there will be, but it will be very less, and therefore the light energy will be the less. So therefore we can say the logic is that if the mass of the star is very high, then there will be intense fusion reaction. So that is basically the only part that you need to remember, that the logic is, if mass of the star is very high, then there will be intense fusion reaction. Intense means or strong fusion reaction. Now if the star is massive and it has reached to the level of the oxygen and the neon, and still the temperature at the core is very high, then the radiation force will be far exceeding. So means that radiation force means this one. So it is, the radiation force is outwards, means it trying to explode, right? So the radiation force will be very high, and it will be in the excess to the gravitational pull, and therefore the balance and equilibrium that we are talking about, that they both balance each other, that balance would be, will deviate, and the balance will be more on the side of the radiation force. So it will completely upset the balance, and the star will explode. So here, so I hope you got the point, that if the star is very heavy and the fusion reaction is very high and it has reached the oxygen and the neon level, and it's still very hot from inside, then the star will explode because the radiation force has been increased. The balance is upset now. Now this explosion will break all the shell and leave behind the core as a recoil, as the Newton third law said, and that will become the daughter star. Now, in order to make sure this daughter star, because for every star, it depends that whether it will explode or not. So in that case, the Chandrasekhar was actually a scientist who gave the Chandrasekhar limit. Now the Chandrasekhar limit basically is that it said, if let me write it here itself, or here, Chandrasekhar limit. This is regarding a white dwarf star. So dwarf star is basically what the daughter star had become. Now daughter star can either become a dwarf star or it can become a black hole itself. So what Chandrasekhar limit has said is that if for a particular star, if it is solar mass is 1.4 to 1.5 times, 1.4 or 1.5 times, if for any star, if its mass is less than 1.4 or 1.5 times of solar mass, then it will be, it will be halt at the hydrogen to the helium. It will convert to hydrogen to the helium, and then it will halt. So it won't be anything. So the original mass of any star is equal, then the nuclear reaction will stop at that stage and there won't be an explosion. But if the mass is more than 1.4 to 1.5 times of the solar mass, then it will explode. So this exploding of the star is what we call as the nova. Nova. So the core that is left behind the daughter star is what we call as a white dwarf. So I think it's pretty much straightforward that if a star mass is 1.5 times greater than the solar mass, then it will explode. This is called the Chandrasekhar limit. And when it explodes, it will leave behind a dwarf star, which we call as a white dwarf star. So that is pretty much regarding the Chandrasekhar limit. And similarly, the white dwarf star, sometimes there is also called the yellow dwarf, whose mass is actually very less than the Chandrasekhar limit, that is less than 1.5 or 1.4. Then in that case, its nuclear fusion reaction will stop at the at a very early stage, so that not much electromagnetic radiation will be released. It will be very weak, so therefore the less light will be there. So in that case, it becomes the yellow dwarf. And interestingly, our sun is actually the yellow dwarf. It will become after some million of years, because our sun is not very big. Actually, its mass is less than 1.5 times. So our sun, if it explodes in the future, it won't convert to the black hole, so it will become a yellow dwarf. Now in the massive stars, the fusion fuel will be depleted very fastly because it's massive, the whole much amount of fusion reaction taking place. So obviously their fuel will deplete very fast, and because of the rate of fusion is rapid. Now when the fusion will come to the end, then star won't look so bright anymore. Obviously, because nothing is left behind that star anymore. And by this the fusion may go beyond the stage of the oxygen and the nitrogen, or sorry, the neon. So there is also one more, the graph which has been provided, which we call as a Hartspring-Russell graph. So, so it actually appeared to be like this, that if this is a brightness, or we can say a magnitude, and this is color. So, okay. So this is a what we call as a bright zone, and this is basically the main sequence also. So whichever is in this zone, for example, like sun is right now here. So what we call is, it is still a bright zone, means the sun is shining. So this is basically the graph what it says. So the most of the star falls in the main sequence. So any star in the main sequence is very bright, simple as that. And brightness is because of the two reasons. The star may be young and the fusion reaction taking place in that. So even if the star is not very massive, it is little old, but still the fusion reaction is taking place, then also it looks bright. So the massive star will not stay in the main sequence for a very long time. So the sun won't be here for the very long time, because the fuel will deplete very rapidly and it won't be bright anymore. So sun is not a massive star in the solar system. It will spend 10 billion years in the main sequence itself, whereas massive stars won't stay that much here. So this is what we call as the Hartspring-Russell graph. So let me write it here. Hartspring-Russell graph. Yes, you can rewind this video again if you haven't understood, because that's pretty much crystal clear. Now if there is a massive star whose value is actually much greater than Chandrasekhar limit, its nuclear fuel will deplete. As we have discussed earlier, the fusion reaction will be slow and it becomes fainter, and finally it changes into the red dwarf. Now no more electromagnetic energy. The star will finally become a dead star, or a body of just a rock. So it's a star's death when the fusion reaction come to an end. But if the star is massive, it goes beyond the stage of the oxygen and the neon. It will give birth to the magnesium, then later on the iron will be the next stage, and finally comes to an end. And more importantly, the final is actually what we call as a most stable state, because that is actually the last stage. And this is where the explosion occurs. So we say generally, actually, when a massive star undergoes a very high fusion rate, and because of that its fuel will deplete very fastly, and it crosses from hydrogen to helium, from carbon, then oxygen, then neon, and finally it reaches to the iron stage. Alright, and still it is very hot. It will suffer a massive explosion, and this massive explosion is what we call as a supernova explosion. Now the recoil will give birth to the daughter star, and that is called the neutron star. So here, due to recoil, it will give birth to neutron star. Now it is called neutron star because it is dominated by the neutrons, very specifically, and it is very dense, and the enormous amount of the matter in it is very small volume. So that is why the neutron star is super dense star. And generally, the gravitational waves actually reached to us the last year, I think the previous 2017, I think it reached to us after 3.5 billion years. So these neutron stars actually are of the diameter of 10 to 25 kilometers as the mass of the regular star. The interaction between the electrical and the magnetic field, because of this the fusion leads to the interaction, and the great gravitational pull at the center, this results into the formation of the X-rays. So that's why we call the neutron stars actually a great source of an X-ray. And because of these X-rays itself, we are able to determine the neutron stars. So whenever we have a molten core, for example like Earth also, automatically the magnetic field will be formed, and these magnetic field will attract the electric field, and because of that then X-rays will be formed. So this is pretty much like that. So the X-rays are trying to leave the neutron stars, are bent again to the center because of strong gravitational field, and these X-rays are going to escape from the polar region, similar like our planet. So if this is the core of our planet, and this is a star itself, and because of the electric and the magnetic field, most of the radiations will pass through here, and because of the intense density, electric and magnetic field, this will result into the X-rays, and so the X-rays will transfer in this direction. Here also. So this is where the X-rays are. So this is where the X-rays. So this will what happen, and generally these stars sometimes they are not at the same point. They are sometimes rotating vertically or around maybe like this vertically, or vertically like this also. So right, and if something is happening like this, so what generally happen, and so as we have studied that these are the only point where the X-rays are transmitted. So if something is rotating like this, so whenever this position will point to the Earth, only then we can receive the X-rays. So generally what happens, we receive sometimes, we sometimes don't, we receive, we sometimes we don't, and something this like happens, then we what we call as a pulsating. So it's like a pulse, right? So we call it as a pulsating, or we can say a pulsar or a pulsating star. Pulsating star. And we recognize them on the basis of this, that we get an X-ray, then we don't, we got an X-ray, then we don't, because it is keep on rotating vertically or horizontally. So this is what happened, and this is what we call as the dwarf stars, yellow dwarf, red dwarf, supernova explosions which are happening. Then we talk about the black holes. So we'll study about the black holes in the next chapter. Thank you.